Hi everyone, my name is Ecem Layra Görk. In this presentation, I will going to talk about the studies I have conducted with Middle East Technical University EEE STAR program. The project is entitled as Adjusting and Testing a Drift-Diffusion Model for Heterojunction Solar Cells, Simulation for an Ion Diffusion Media. My project supervisor is Professor Selçuk Yerci and my mentor is Cem Şahinar. Bertay Eren, Tuğçe Şevvalkaya, and Aykut Sarıkamış are also the undergraduate team members who contributed to the same subject. First, let me introduce my outline for this presentation. In the first part of my talk, I will going to explain the studies made during the summer internship period. This first part is also reported under the scope of EE 300 summer internship course in detail. The second part, however, will be related to the studies made after the summer period study and not explained in the scientific report. The majority of my summer period study was related to the previous EEE STAR project which has been conducted by Kazım Batuhan Karaman. In his project, he has developed a drift diffusion model for two-layer heterojunctions. A drift diffusion model for the carriers inside a semiconductor can be illustrated as in Figure 1. In this phase space representation, the constant momentum motion of a carrier is called diffusion and constant position motion is called drift. Collisions and generation recombination mechanisms also take part inside the semiconductor. A drift diffusion model models the relatively simplified motion of carriers inside the semiconductor. For the simulation purposes, continuity equations for the carriers and the Poisson's equation are simultaneously solved. The mathematical background of the model is explained in detail at reference 3 and is summarized in my scientific report. Based on this background, I have conducted my studies. After studying the previous material, I have moved on to implementation. First, some little bug fixing is made related to the constant generation rate and the Shockley-Reed-Hall recombination mechanisms. Then, a third layer, a mid-layer, is introduced to the model. After this implementation, the code is now capable of simulating PIN, PPN, or PNN type designs, provided that necessary material and thickness parameters are provided. Here, on the right in Figure 3, a three-layer heterojunction band energy diagram can be observed. This figure is obtained by the modified simulation. What is more, a power calculation model is introduced to the model. After this implementation, open circuit voltage, short circuit current density, maximum power point, fill factor, and power conversion efficiency with respect to the AM 1.5G standard spectrum illumination can be calculated for any design. After the implementations, now it is time for testing. To understand the outputs of the modified heterojunction code, another drift diffusion solver for heterojunctions is used, which is called Solar Cell Capacitance Simulator, SCAPS. SCAPS is a one-dimensional solar cell simulation program based on a drift diffusion modeling. As a test case, the sample study in reference 5 is selected. Some parts of the study in reference 5 is reproduced both in SCAPS and in the modified code. Then, the outputs are investigated for band energy diagram at equilibrium and with the presence of constant generation rate, carrier distributions, JV characteristics, and for the generation and recombination mechanisms. The power calculation module is also tested by SCAPS. Here, at the table on the left, one can see the solar cell operation-related parameters obtained by the modified code. At the right uppermost figure, the outputs given by SCAPS is presented. As can be seen, the results correlate. Since we have observed the outputs, now we can discuss on the results. SCAPS has more capabilities than the modified heterojunction code. However, in general, the results of the both are similar. Since SCAPS has more simulation capabilities, the SCAPS model is constructed so that most satisfying results can be obtained from both. However, there are some differences due to the model nature. The major difference is the way how recombinations are introduced to the code. In the modified heterojunction code, the only recombination mechanism is the Shockley reed-hole recombination mechanism. No matter what the carrier type is, a single recombination value is calculated per space mesh, according to the carrier concentrations. However, for the SCAPS is only able to simulate Shockley reed-hole recombination when neutral defects are introduced to the semiconductor. Even though the distribution of the deep defects is selected to be uniform, electrons and holes are not equally trapped by these states. In Figure 10, we can see that the occupancy probability of electrons is almost 1 throughout the junction. However, this probability is almost 0 for the holes. Therefore, this difference affects the carrier distributions and changes the recombination rate. The next study topic is related to the ion diffusion phenomenon observed in perovskite solar cells. Before giving the details, I would like to explain why perovskite technology is a groundbreaking topic of the perovskite industry. Perovskite solar cells have shown a power conversion efficiency of 23.3% at 2008. This efficiency has exceeded the past best efficiencies recorded from 6 cadmium telluride and silicon-based solar cells of the past. What is more, Oxford Photovoltaics has recently announced a 28% efficient perovskite silicon tandem-based solar cell. Even though perovskite-based designs can provide high power conversion efficiencies, inside those devices, not only the carriers, but also the ion seems to be mobile. In long term, the ion migration also affects the power conversion efficiency. The ion diffusion has been suggested to be the primary cause of the current voltage hysteresis. For overcoming hysteresis, surface passivation methods have been discussed. Even though surface passivation helps to overcome hysteresis, according to reference 2, the primary outcomes of the ion diffusion in such devices can be observed even when the appropriate surface passivation is made and hysteresis is minimized. In Figure 11, mobile vacancy and immobile anion concentrations inside perovskite is displayed. This characteristics is extracted from the open access MATLAB code developed by reference 7. This distribution is then studied. Since the vacancies and the anions compose the majority of the particle distribution in the Drift-Diffusion model, their vast distribution affects the potential distribution inside the material. As explained in the mathematical background of the model, by solving the equations, what we want is to find the potential drop at each mesh space. We want to obtain not only the band energy diagram, but also the JV characteristics from the simulations. The open access MATLAB code of reference 7 cannot provide the JV characteristics. Then, from the intermediate steps of the code, vacancy and anion distributions are extracted, as in Figure 11 of the previous page. The distribution characteristics is first exported to SCAPS for further study. However, SCAPS failed to converge to a result. Then, based on the principles introduced in reference 1 and 3, a discretized, linearized, and normalized Poisson's equation that is seen in equation 1 solver algorithm is developed. The code imports the anion and vacancy distributions, then performs iterative converging. The flow diagram of the code can be seen here. However, even at the equilibrium conditions, this method failed to eliminate the electric field inside the bulk. Therefore, for the upcoming studies, another open access simulation is preferred. In this part of my presentation, I would like to talk about my studies after the report submission. In this part, our aim is to find how the cell responds to different frequencies. Using the open access powerful Drift-Diffusion model, Drift-Fusion, a testing environment is constructed for impedance spectroscopy measurement. Basically, the impedance spectroscopy is a measure of impedance throughout a frequency spectrum. The carriers inside the cell respond differently for different frequencies. In this model, first the cell is taken to open circuit voltage conditions at steady state. After steady state is reached, a small alternating voltage with a DC part equal to the open circuit voltage is applied. The same process is made for a large frequency interval. For each frequency, the alternating current is observed. For each case, the magnitude of impedance is calculated from the ratio of the peak-to-peak values of the voltage and current waveforms. As can be seen from the figures on the right, as frequency increases, the phase shift between the oscillations increase. As frequency increases, the cell starts to be more capacitive. Knowing the magnitude of the impedance and the phase shift, we can find the resistive and the capacitive parts of the impedance. The first studies are made by considering the ions to be stationary. On this page, some outputs of the study are displayed. In the figure on the left, the LCG plot can be studied for different frequencies. As frequency increases, the cell starts to act more capacitive. Due to the high frequency, the carriers cannot move, hence they become stationary. The charge accumulation creates a capacitive response. As frequency increases, the settling of the simulation also becomes harder. Therefore, the current waveforms fluctuate. At the figure on the right, the magnitude response of the impedance is displayed. As frequency increases, the magnitude of the impedance also decreases. The capacitive characteristics dominate the cell behavior at larger frequencies. Finally, before concluding my presentation, I would like to talk about the future study plan. Now, I am working on the impedance spectroscopy measurement. The existing simulation will be modified so that the phase shift between the voltage and the current waveforms will be calculated automatically for each frequency. After finding the phase shift, the capacitive and resistive characteristics of the cell will be determined. This simulation will be optimized so that using the Drift-Diffusion, a Nyquist plot for resistive and capacitive behavior will be obtained. Drift-Diffusion can perform simulations both for mobile and immobile ions. Then, after constructing the optimized simulation for immobile ions, the same simulation will be performed for mobile ions. Now, the simulation is based on the default material parameters of the simulation. After constructing the model, the same simulation will be ran for real design and provide simulation data for impedance spectroscopy. Next, the impulse response of the cell will be studied. Then, for every frequency value, a data will be obtained. This last part concludes my presentation. I hope it was enjoyable. Thank you.